and we can get this thing down to 0.02 of a mil. But there's also a scan area tolerance as well. So we could do a 1 millimeter scan, and it's basically looking at 1 millimeter squares all over the surface.
Yeah.
Or we can take that right down to 0.2, 0.1, whatever. But your scan time and file size is increasing as well.
I think a common misconception with 3D scanning these days, with those who haven't used it, is that you scan something and then that's just going to give you a perfectly finished solid CAD model that you can reproduce from there in your CAD software. There's obviously a few steps in between that, and one of those is using a software package like what we're looking at behind us here. Can you talk us through that process, what the software package is and how you kind of use it for the work you do?
This is the VX suite of softwares from Creaform. We use the Black Elite system here internally. Time is money, right? So we're not going to sit there and scan things that we don't need to. We're not going to waste time on that. And normally 1 or 2% of the time have I taken an actual scan and put that directly into a printer. So it can be done, but you just simply don't. The main problem with that is that you take any imperfection from that part and you just carry that straight through. What we want to do is obviously we want to go back to having things symmetrical and even and engineered, if you will, unless it's an organic shape. So we're only normally interested in certain parts, like it might be a bolt face and therefore the centers of where those bolts are, and then we'll create the entities in the software. So we'll be selecting mesh faces and letting the software generate those center lines and that for us, and then we're exporting that out into CAD, and then we're modeling over top. That's to say 98% of the way we do it.
So if we talk about those entities, just can we clear up what exactly that would be in this case?
With anything, if you had a mounting face, then I just want a flat face.
Yeah.
So I'll select as much as I can. I'll put a tolerance on my selection.
So a planar surface.
Yep, just an absolute plain surface, dead right. I may want cylinders on bolt holes, so I'll select those curved faces, and then that'll, again, approximate out on the tolerance that I've given it and give me the center line for that. I can take cone features if I want. I can take cross sections. Sometimes you want to know, literally what something looks like through in the middle if you want to extrude off that or what have you. But they're the main ones, or maybe just simply a point. Yeah.
So the key geometric features from the scan data.
Yep, dead right. Yep.
And you're drawing that out. So why do you need to do that in here and not your CAD software?
It's mainly the accuracy of that initial measurement, and it's, can you even measure it to start with? Okay. It's when we use it for in some QA scenarios as well. You physically can't caliper some things. So if I use the scan and I use those entities and bring it straight in, then there's no human error in that measurement. Maybe you're off that little bit, or you haven't got it quite in the right place. You've got that check and balance. Yeah.
I mentioned at the start as well that people think that the scanner just gives us this great solid model we can work with, but the mesh file is a little bit more difficult to work with. Does that factor into a software package like this? Is it just, it's designed to work with that mesh file, right?
It blows my mind how good that is. We deal with meshes from the printing side, so we're very used to good meshes and some pretty horrible ones. Got to keep in mind that a scanner is a line of sight thing. So if you've got anything that the scanner can't see, well, now we've got to start fixing and repairing and filling holes and what have you. And it's not just filling a hole as a flat. What's happening around that? What sort of tangent faces are we dealing with? And that's where this software is so amazing that when it fixes a hole, you actually don't know it's been repaired. It just picks up that surrounding area and does such a good job. And then even if you get a bit of noise in the scan, which you can get, it takes out those peaks and it cleans the mesh up, and it's pretty impressive.
A lot better at working with a mesh file than like a dedicated 3D modeling software, essentially.
Yep, right. And I think that's the other thing is sometimes when we do scan jobs for people and they say, can you just send me to that as a step? Yes, we can do an auto surface on this, but you've just got to remember that it's then deriving that off a mesh as well. So it's not going to have just nicely trimmed edges, and it's not going to be a nicely editable thing, which is why we tend to model it. So we've got a much more useful and easier model to edit.
So you bring those entities into your CAD software, use them as references for building a parametric CAD model from that then you can recreate identically and really good quality, or also modify, I guess, from there as well if you need to. So then it might be that's just your starting point, and then you need something different. But design another part off it, or recreate it and change it or something like that.
Right.
Cool.
There is instances where and softwares are getting a lot better where they can go through and start to do automatic features and start to extract what they, if it's obviously it's a revolve or it's an extrude, and it'll create that for you, but it's still putting it back into a CAD model.
Yeah.
It's not like it's making the scan useful, it's still a model generation.
All right, so that's one kind of use for the software, but you mentioned QA before, quality assurance, I guess. What would that process look like? You're scanning a part that's been manufactured and then comparing it to the original CAD model?
So we're lucky that our workflow here is digital start to end. So it means that we've got the input file that goes into the printer, for instance. So when we've got a part at the end and we scan that, and then we can overlay the two and actually see where any variations may have occurred. Or we can, again, if it's an area that you just simply can't measure with a caliper or vernier or whatever, you can start to just take those measurements off and use it as a QA. Yeah.
Cool. So a key kind of question that would come up, I guess, is if the scan itself is not accurate to the part you've scanned, then how do you know that's going to give you the right kind of idea of the accuracy compared to the real part? What type of accuracy can you expect out of the scanner? Is that something as well that you need to be careful about how you're scanning to control?
Yeah, you do. There's two sort of tolerances that we concern ourselves with. There's like an ultimate tolerance and we can get this thing down to 0.02 of a mil if we need to, but there's also a scan area tolerance as well. So we could do and it doesn't sound like a lot, but a 1 millimeter scan, and it's basically looking at 1 millimeter squares all over the surface.
Yeah.
Or we can take that right down to 0.2, 0.1, whatever. So what that means is any variation over that area, it's being much more sensitive about, and therefore the accuracy of that model is increasing. But your scan time and file size is increasing as well.
Resolution and accuracy are two different things, but resolution does factor into the accuracy. If you're talking about, lots of big steps, it's an approximation between those points, and that's where your difference comes from.
Yeah, and like anything, it's what am I trying to do? What am I trying to get out of it? Yeah. What's the most pragmatic way to go about it?
Cool. Yeah, awesome. So we've got a few parts down here, a plastic printed part and then a metal 3D printed part that's been machined up. Can we just talk through what they are and the kind of process that you went through to design this, and then I guess do QA on it as well?
Yeah, absolutely. So we've been really lucky to be working with Change Fuel Technologies on their dual fuel hydrogen project. So this is a hydrogen injection manifold. This particular one is for Dodge Ram, which is a pretty cool vehicle that they've done. So the process that we did with this is they actually gave us the gasket that this went on. So I took the gasket and scanned it, and then all I cared about out of the gasket was obviously the internal diameter, the hole centers, and the outside profile. Took that into CAD.
Sorry, did you scan that 2D?
No, I actually did it 3D, but did a very thin cross-section and essentially exported a 2D. Then took that into CAD, had those critical points, and then just modelled over top of that. So the rest of it was generated manually, if you will. And then printed the first prototype on the SLS machine. As you can see on here, we then took that to the vehicle, and then once you looked at wiring harnesses, and we looked at fuel lines, and we looked at all the other bits and pieces, and can we trim this up a little bit? So there's the feed. Let's call that a design review. Come back, can we make that a bit thinner? Absolutely. So cost to do that's bugger all. Cost to do that is obviously much more. So much better to do changes at this stage. And then that reflected into the final part. So this has been printed in our M789 Mirage steel on our metal printer.
Can we just talk about some of the features of this part that are specific to additive manufacturing?
Anything that's additive, especially with manufacturing, you've got to have a reason to do it. It's at the end of the day, additive's actually a slow, expensive way of making parts compared to conventional manufacturing. So why are we doing it? There's internal geometries in here. So there's a gallery that goes through in here. I won't go into the detail of that too much because it's proprietary to these guys. But to achieve that geometry, this would have to be a massive machine fabricated type component, and then we're starting to lose size. So the ability to incorporate that internal geometry in here is the reason why we've gone about it. Yep.
And then just bringing this back to the 3D scanning topic, you can then 3D scan this at the end, run it through the software, compare it to the original model, and check out the quality that you're getting out of it.
Exactly right. Yep. So we can overlay those two models and then literally run through an analysis and show us where our variations are.
So this being a printed part with a few machined details in it, how close would you be getting to the original model?
With printing, we sort of reliably say that we're sort of 0.3 of a mil with the printed part.
Okay.
And then different machine features on here, depending what they are, whether it's so the injectors come in here on an O-ring, we're getting them at 0.05 of a mil. And that's why those faces are machined.
Yep.
Because it's just a tolerance that we can't hit with printing. And also there's a surface finish that's better than what we can get on printing as well. So high tolerance there, but generally, 0.3 is pretty reliable for printing.
Awesome, cool. I think that gives us all some insight more into the process of actually scanning to a real part, and then also some prototyping through to 3D printing metal, and then backing that up with 3D scanning for quality assurance at the other end as well. So thanks for that. If people want to follow along with the type of stuff you're doing with this, where are they best to do so?
Website's the easiest, so fiadditive.co.nz, and there's a section on here, scanning services on there.
Perfect. Thanks for your time.
Pleasure.